Hello everyone, thank you for joining me today again. My name is Triangle Anderson Gadget. You can call me Turn or Dr. Turn, that works for me. We're going to be picking up where we left off from the last video. Let me stop this can and then we'll get on to it with it. Okay, so now this is the last time we just predicted the y values, and then we viewed briefly the first set of rows. Today we're gonna but this came out as an array. We'll have to flatten it so that we will go ahead and compare with the actual values. So let me begin by say flatten y spread, that is from 2D to 1D. You got to compare apples with apples, right? So let me just say y spread flat. I will just store it as y spread flat is equals to y spread flatten. That should be that. And then I will flatten. I'll just say flatten y test now. Remember how we created the y when we are trying the data set to is a data frame if is instance y test PD data frame, then y test flat equal to. Okay, let me pause this and then type this code because it's going to be relatively long to save time. Okay, so this is what we have. We first of all we flattened the y spread. We stored it as y spread flat, and then we did the same for the y test data frame to make sure that we flatten it as well. After that, we set the index to align. Again, you got to compare apples with apples, right? And then we combine the data into a single data frame. Here, then we took the difference between the y spread, the actual, and minus the predicted values to find the difference. Here, then we displayed the output in a table, and around that, this is what we have. These are the differences. The first set have minor differences, but I'm seeing a large one, large ones down as we come down further. So that is the output. This is just the top 15 records. I usually like reviewing the first 3-4 records, but for the sake of demonstration, I wanted to show more. Next, we will be viewing the let's view the evaluation model. Let's see if okay. Evaluation model. Did I tell that right? Evaluation model performance with metrics. I think this is not markdown. That's why that is behaving like that. So let me just hit M on my keyboard to change it to markdown. That works now. Now I'm going to come over here. Then let's enter that as, first of all, this looks like a markdown now. So go back, hit Y on my keyboard. I think that should work. Compute mean absolute error, error, MAE, that will be equal to mean absolute error. That's why I like VS Code, because it kind of has some predictive feature in it that helps you as you're typing. I love it. Now that should be that, and then next we're going to be compute the mean square error, mean squared error, and then let me just include the acronym here. Mean squared error. Again, just copy this up here. Then I'm going to paste it right down here to make things easier, smooth. Next, many people compute only this and leave that. I don't like that. So it's because you cannot really tell what is going on. It's good to also follow that up with root mean square error. Root mean squared error, RMSE, which is also known as, that is squared root of MSE, because of squared. I think, yeah, square root of MSE. That is fine. So that will be our MSE equals to, I think that has to, we have to use numpy to get that, because numpy helps with the calculation. MSE, and then we'll have to compute this R squared. Score, which is R2 R square again. I'm going to come up here, just copy and paste, make my life easy. Okay, now let's run that and see if it works. Perfect. But we can't view the output, so we're gonna have to manually view that. And because I like aesthetics, I usually like kind of like do this is a habit. Times 50, and then down here I will type print model performance evaluation metrics. Let me pause this video and then type this to save time. Okay, so this is what looks like. So basically what I typed down here, I am just trying to display what was here. Remember how I ran this, but nothing, it ran successfully, but we couldn't view, hey, what actually happened. We couldn't see that. So if I run this now, you see that kind of like displayed everything. Just use the round here to shorten the numbers for us to see. Mean absolute error of 4.98 means that there are 4.98 units of insulin, predicted values of insulin, that deviated from the actual values. The mean square error says that, hey, we have about 57.745, if you approximate it, units of squared error that deviated from the predicted value. But again, this can be large, but it can also how can I put, like, dissuade you or not make you see the real picture. So it is always good to follow that up with square root of mean square. Actually, I think I should have used this root Let me change that to maintain consistency. I should have used this here. Then let me run that again. Yes, so the root mean square error, tells us that there's about 7.6 units of insulin that deviated from the predicted values. The lower this number is, the better. In fact, if it is closer to the mean absolute error, the better. Uh, it would be wonderful, because it means that our model prediction is performing very well. And then the R square, many people think that the R square indicates that this is how your model performed. No, that is so wrong. The R square tells you the fitness, how it fits, how the to what extent does the model predict the criterion variable, the variability in the dependent or criterion variable? So that means that we only accounted for 35%. The remaining 65% could be accounted for other variables that we do not include in this model, which gives room for further research. And I think this is kind of like low to moderate as well. Uh, Now, how can we do this? To improve, we can fine tune this. We can also include other variables, or we can also create interaction terms to see if we can, like increase this. But what we can do is, in my part two, I'm gonna be creating interaction terms. To see if that will improve how this model will predict uh, insulin. Another method is to improving this is to try using non-linear models, like random forest regressor, support vector regression, or gradient boost, methods such as XGBoost or LightGBM, something like that. Uh, so overall, I would say that yeah, it's not a poor model, but it's kind of like fair or relatively weak. In my next video, I will uh, explain how we can use interactive terms. We will develop composite variables and see how we can run another regression that will be moderated uh, regression. So if I come up here, we will use the Andrew Hayes' model to develop this. I'm just assuming this is the hypothesis. We use age, gender, and body mass. So we're gonna see how these will interact with the BMI. Gender will interact with BMI, and then the interaction between age, gender, and BMI. This will all be new the interaction terms to predict that, and then we'll compare this model with what we have on here. Thank you so much, and have a nice day. Looking forward to see you next time. Bye.